Good morning, ladies and gentlemen. So we're going to go over just the one part of the problem that was suggested on Google Classroom, and that is 2005 AP Calc free response questions 5D. Okay, so this problem starts out with a graph of velocity over time. And part D asks the question, find the average rate of change of velocity over t equals 8 to t equals 20. And then it goes on to ask something about the mean value theorem. So we're going to go ahead and first focus on the first task, which is finding the average rate of change of velocity over this time. So the average rate of change of velocity is another way of saying what is the average acceleration, right? The rate of change of velocity is your acceleration. So in essence, we are interested in, so here's part D, we are interested in the average acceleration from t equals 8 to t equals 20. That's what this question is, the first part of the question is asking. All right, so basically, if we want the average acceleration, the average value of a of t over t equals 8 to t equals 20. Remember we defined the function in calculus class that to find the average value of any function, we integrate that function over the particular time period of interest, and then we divide by the length of the interval of time. Okay, now what this numerator is doing is I forgot my dt. This numerator is essentially adding together a whole bunch of accelerations. So we're adding infinitely many values of acceleration. So we're getting a sum of all the accelerations over this particular time period, and then we're dividing by the length of the time period. Similar to like a discrete average where we sum together all the values and then divide by the number of values. So this is the sort of continuous analog of that concept. Now, so if we think of it in this way, you might be wondering, well, we're given the velocity graph, so how are we supposed to do this? Answer a question about acceleration and integration of acceleration when we're given velocity. Well, fundamental theorem of calculus part 1 tells us this numerator will be expressed as the antiderivative of acceleration evaluated at 20 minus the antiderivative of acceleration evaluated at 8. Of course, the antiderivative of acceleration is velocity. So I'm going to go ahead and rewrite this as v of 20 minus v of 8 all over 20 minus 8. Now this should look familiar to you. This is actually, if we look at the velocity graph, this is just a slope. The numerator is a change in y, the denominator is a change in x. So I'm going to go ahead and actually identify those points. Here's the first point. This is the point 8, 20. And I need to be able to identify this point. So I know the x coordinate of this point is 20. I don't quite know the y coordinate yet. So let's go ahead and do some side work before we can answer the question below here. So basically, in order to determine the y value here, I need to determine the equation of the line that this point sits on. All right, so, well, that just means I need to determine the slope and the y-intercept of that line. So I'm going to take two known points on this line, so 1620 and the point 24, 0. Those 2 points lie on this line, and therefore I can determine the slope of this line. So the slope of this particular line is, all right, so I'm going to do change in y over change in x. And this gives us, ultimately gives us a negative 20 over 8, which of course is negative 5 over 2. Okay, I'm going to put this into slope-intercept form. So I know that the equation of this line can be written as y equals negative 5 over 2 x plus whatever the y-intercept is. I don't know what that is yet, but I can solve for it by choosing a point on this line that I know. And I'm going to use the point 24, 0. So 0 is equal to negative 5 over 2 times 24 plus b. This ultimately leads to the fact that b is equal to 60. Okay. And so really the equation of the line is y equals negative 5 over 2x plus 60. All right, again, let's remind ourselves why we just went through all that. We're interested in this y value over here. Now, how do I determine that y value? Well, now that I know the equation of the line that that point sits on, I can plug in the x coordinate and get the y coordinate. So y equals negative 5 over 2 times 20 plus 60. All right, and this leads to, if you go through the algebra, y ends up being equal to 10. Okay, so that's the y coordinate that we're interested in. That's our point. It was actually, I'm realizing now, a lot quicker. You could have figured that out a lot quicker. The x coordinate is halfway in between 16 and 24. And so, you know, since the y values are changing at a constant rate, you could have easily have determined that the y value was 10. But anyway, as far as all the work that I just did goes, it is definitely important to be able to find the equation of a line and being able to plug a known coordinate to get an unknown coordinate into that equation. So I'm glad I went through the process anyway. So let's move on. The reason we needed that information now was to finish the first part of this problem, part D. So V of 20, as you can see, is 10. V of 8 was 20. And 20 minus 8 is just 20 minus 8. So finally, the average acceleration over t equals 8 to t equals 20 is equal to negative 10 over 12, which of course is negative 5 over 6. And now we should include units. So this is an acceleration, right? So even though we're looking at the velocity graph, what we did was we found the slope of a line, of a secant line along that velocity graph. So here's the secant line that we just found the slope of. And so that change in y was meters per second. The change in x was second. So our units are meters per second per second. And that makes sense because we should be finding an acceleration. So the units check out. Okay, so there we have it. That's part one of this problem finished. The next question, this question goes on to ask, does the mean value theorem guarantee a value C, so some x coordinate between 8 and 20, can we guarantee that V prime of C is equal to this average rate of change? So in essence, we want to know, is there a derivative along this curve that is equal to the number that we just found? Another graphical interpretation of that is there a tangent line slope that is equal to this secant line slope that we just saw? And just by kind of like sketching here, I'll use some blue lines to sketch some tangent lines, choosing points between 8 and 20, you can see that the tangent lines are all either horizontal up until this corner here, and then they just become the slope that we found earlier, which was -5/2. That being the slope here of this line. So you can see just by analyzing that, no, there's not gonna, there won't be any tangent line within this interval that is equal, that has a slope equal to -5/6. But how do we argue that officially? Well, recall the definition of the mean value theorem. This is the mean value theorem definition. It says that if we have a function that is continuous on the closed interval and differentiable, meaning that a derivative exists over that interval, then we will be able to find a tangent line slope that is equal to the secant line slope. Okay, now our situation fails that definition. Why? Well, that definition said that our function that we're analyzing, which in this case is velocity, has to be continuous and differentiable on this interval. Well, velocity is definitely continuous on this interval, but we know that it is not differentiable. I cannot find the derivative of velocity at this point right here because of that corner, right? We learned earlier, much earlier in the year, that if a graph has a corner, we cannot find a derivative at that corner point. And it has to do with the fact that the limits of the tangent lines sort of jump from, and as you can clearly see it, the tangent lines jump from 0 to -5/2 in an instant, okay? And since there's not like a smooth continuous transition of slopes, we call that a point of non-differentiability. Okay, so we would answer that the mean value theorem does not apply. In this situation, because v of t, the function that we're analyzing, is not differentiable at, and let's tell them the exact location, at t equals 16 seconds. Yep. Okay, and there you have it. That's problem 5D. A pretty involved problem, but once we get down to like part C and D of these AP problems, they definitely become somewhat involved. This one required a few steps to solve, and that's how they end up going. That's the structure. So anyway, ladies and gentlemen, I hope this is helpful. Of course, if there are any questions, let me know. I'll be posting another suggested practice worksheet today, and I would really love it if I get a lot of people suggesting problems for me to go over. But anyway, I hope all is well, and I will talk to you again soon. Take care.